We shall pick up then. There's Mr. Laptop. Ta-da, creepy screen. Here we go. So, in general, I have my answers in here as always. What role do time invariant predictors play in the model for the means? What did you guys come up with? Effect on people things, yes. Such as, like what kind of people things? You talking about predictors or people things, or outcomes or people things? Outcomes? Okay. Like, someone help her out. What kind of outcomes that are people things? Can you come up with like a statsy word that means that? Blank effects, maybe? Outcomes. What are the time invariant predictors predicting? They have fixed effects in predicting what? What kind of variance? She said people things, and she's right. But I'm going with more words here. Random, that's the magic word, yes. So time invariant predictors are people level variables, which is level, please get it right on the last day of class. 2, hooray, we've got it. Until next semester when we change up all the levels, because levels are always study dependent. But for today, damn it, level 2 is people, level 1 is time. So time invariant predictors are people things that predict people outcomes, otherwise known as random effects variances. So intercept differences, slope differences. The only kinds of slopes that we've seen so far are related to time, but you can also have random slopes for time varying predictors. Anything that's measured more than once for a person, that's what they do. Indeed. Specific effects, I think that was the next one. How do you think about effect size and significance for a specific effect, such as the main effect of a time invariant predictor on the intercept? How do we tell significance? Wald test, otherwise known as stare at the p-value, right? And why is that perfectly fine to do regardless of whether you're in ML or REML? Why is that okay? They're fixed effects. They're fixed effects where a null hypothesis of 0 is a plausible thing, and the fixed effect can go either direction from 0. It's not on a boundary. So using a two-sided sampling distribution given by either t or z, estimate over standard error, p-value, all that's cool. So you get one p-value that goes with each time invariant predictor's effect. If you had something like a grouping variable, like if I had education group on the intercept, does that change your answer any? Same idea, different part of the output. So let me show you an example from what we looked at last time. We did have education group predicting intercepts and slopes. So if I have 3 education groups, their main effect is what predicts the intercept. And right here, I get education group differences in the intercept, in the main effect here, of each alternative group relative to one reference group. That's one set of p-values. I am missing one of the comparisons, which I asked for via an estimate statement, but I also get this output down here anytime I use the class statement, which is there an effective group on the intercept across all 3 groups? It's a 2-degree of freedom test. Are there any group differences on the intercept? I still think of that as a specific test because it's education group on the intercept. So there's one model parameter that the groups are trying to predict, group differences. How about if I asked, like, does education matter? Next question then, how do you think about, oh, I didn't do the second half of the question, I'm getting ahead of myself. So you got that part, significance. How do we think about effect size then that goes with that Wald test? A specific effect size. Like what is the effect size of education group predicting the intercept? It's the one with the funny name. Pseudo R squared, yeah, and that's not me being funny. That's like what it's called. That's what everybody has agreed to call it. Why is it pseudo? It can go the wrong way, yes. But pseudo means per variance component. So I can talk about the specific effect size for how education predicts the intercept by the amount of intercept variance that has been reduced relative to some comparison model. Now the third question, does education matter? So in this example I had education predicting the intercept and each of my piecewise slopes. How would I assess significance and effect size in that context? That's my multivariate wald test. That's the one that you have to do yourself. So in this example, this is 6 degrees of freedom because there are 6 fixed effects of education. You would list each one separated by a comma per degree of freedom. So if the variables for which you were asking for this multivariate wald test are continuous, it looks like this in form, where you just list the continuous predictor followed by a 1 and a comma. You would list any interaction term in the same way, 1 and a comma. If it is a categorical predictor on the class statement, then you have to list contrasts. So there are as many numbers as there are levels of this grouping variable. So this set of 2 right here, that gives me the main effect of education on the intercept. It's a 2 degree of freedom test. It does not matter which values get the -1 or the 1. I just have to have 2 different contrasts. If I know 2 of them, I can always get the third. So then I did the same thing for each of the slopes as well. So that's how you would refer to the set of multiple fixed effects. If I had just typed these 2 by themselves, those 2, the main effect of education on the intercept, that is exactly what SAS does for me already right here. That's what it's doing. So the code that I wrote that put the 6 together is like testing all 6 of these at once, 3 pairs of 2. That's one way to answer a global question. How does adding education help my model? And last but not least, what is an effect size I can use to support that? If it's not pseudo R square, the other one? Total, I heard you whisper it. Total R square, yes. That is the square of the correlation between the outcome that is predicted by the model fixed effects and the original outcome. So those are different ways to talk about significance and effect size. Any questions on that? Last but not least, would anyone like to share their theme song with the class? Did you all come up with one? Some of you did? Okay. No one wants to share? I'll read them later, okay? Oh, I promise. This is one of my favorite parts, is learning about people's musical preferences. So, yes, indeed. All right, homework. How's homework going? Homework is going? Do you want to go over any of it? Would that be helpful? Any specific questions, or do you want to walk through sort of strategy? Someone in the back wants to talk. Hallelujah. Yes, ma'am. Yes. Let's do that one. Those are tricky. She's like, yeah, I know. That's why I asked. All right. So section 3, I presume? Okay. So by section 3, you have age predicting intercept, linear, and quadratic slopes, and you have meditation group predicting each of the 3 things. And I'm asking a variety of questions about the expected level of well-being for each group at different times, as well as the expected linear rate of change for each group at different times. So give me one number I can use as an example. Yes. 41 and 42? Okay, perfect. Okay, let's grab that. All right. Estimate. Give me the estimate for the linear rate of change at the end of the study for the control. So in each of these questions, the key is parsing what is the root term I'm trying to estimate and which of these words reflect moderators of that term. So in this instance, linear rate of change, that's the thing I'm going to estimate. So holding age constant at 0, I'm going to write out like an estimate statement. Rate of change. That term, what fixed effect in the model matches those words? Time. So call that time. All right. The fact that that is the thing I'm trying to estimate means what number goes after it? 1. From there, what goes in the equation is every fixed effect that contains time in it and none that don't. So let's write out what the model is going to look like by this point, because I think everybody has got a hold of that. So I'll put intercept in here, time squared, and say, actually, let me write it out. Time by time. We have the age stuff, which I'm leaving out because I said you could hold age at 0, which makes everything go away. We have group by time, and we have group by time, right? That's my model. Everything that has to do with time or group, leaving out the age stuff. So if I go through here, if time is the slope for which I'm trying to gain an estimate, that's the one, right? Do I need this quadratic term? Yes, I do. Is the word time in the highlighted portion here? No, so group doesn't go there. Even though it is for the control group, the main effect of group is for the intercept, not for the linear rate of time. However, if I want to know what the effect of time is for control versus treatment, I need that one, right? And if I need that one, I need that one. Okay. Trying to make it smaller so that it fits on a thing, but hang on here. Let me change the layout. There. That's better. I'll bold the numbers so that we can see them. All right. So let's do the first part here. We said this is the linear rate of change. Let's do for the control group. Okay? So that is when group equals what? 0. So any term here that has group in it has to be 0. Hang on, let me put it over here. Okay, now that leaves this one. And I screwed this up on Monday, right, Ejin? I was helping her and I thought we had the right answer and I had to look back at my answer. And I've been doing this for 20 years and I screwed it up, okay? This stuff is not easy. Now, what is the value of time at the end of the study? It's 5. So we put 5 here. And we're like, why didn't it turn green? I don't know. Times 2, that's the part I forgot. Twice the quadratic is how the linear rate of change changes per unit time. So that, my friends, becomes 10. Here, I'm going to abbreviate for control. Can I fit them all? Good. Okay. All right, so I've got my structure here. Let's do it at the end for training. What changes? Well, I'm still trying to get the linear time slope as the thing I'm estimating. That stays the same. It's still at the end. Now I want it for the other group. What is their value? Now, is this 1 here or is this 10? Tricky, right? Because if I put a 10 here, then this one in theory could be a 10 too. But in this case, it's a 1. If group is 1 times time being 1, it's 1. If I go over here though, group is 1, time is 1. This time moderates when the group by time interaction is 4. It gets the 10. Okay. Are you with me? Now, all of my questions are deliberately structured to get you to estimate something and then find the difference between it. So I'm guessing the next question after these two is the group difference in the linear rate of change at the end of the study, right? We subtract group diff in linear time at end. That's what we're going to get here. So the root term is actually this whole thing, group diff in linear time. You can figure it out from that perspective. Which term in my model here does that idea map onto? Group diff in linear time. The effective linear time, excuse me. I gotta be clear. Which of these words up here, these fixed effects, space them out a little bit, does group diff in linear time, the effective linear time, correspond to? Is that one? So I can figure out this one thinking about it from two different ways. If I think about it from this way, if this is the thing I'm trying to estimate, group diff in linear time, it gets the 1. If I want it at the end, well, I got to go back up to my model. What else do I need in here? How many other terms contain group by time in them? Just this one. And then this one should be 10 if it's at the end. So that's one way to figure it out. What? It's at the output for the beginning. The group difference in linear time right here would be conditional on when time equals 0, which is at the beginning. So yes, group differences in the effective linear time at the baseline is right here. Group differences in the effective linear time by the end starts with what it is at baseline, and then it uses this three-way interaction to move it to what it would be at the end. Does that make sense? The other way that you can figure out what this would be without thinking about interaction terms is say, well, I found what the control group's linear time slope should be at the end in the first line there. I found what the, I should change it here. Let's put this as treatment. I found what the other group should be. If I take one line and subtract the other, that gives me my group difference, right? So what is 1 minus 1. 0. What is 10 minus 10? 0. What is 1 minus 0? 1. What is 10 minus 0? That's where we are. So the trickiest part about this is not putting 5, it's putting 2 because it's quadratic. But otherwise, it follows the logic. The key thing that people have screwed up is they forget what the root is, it seems like. So if I say something like, the estimate of the fixed quadratic rate of change for the control group, this is the root. Fixed quadratic rate of change. That is the time by time term. If I have estimate of expected level of well-being at the end of the study for training, the root is expected level of well-being, otherwise known as, give me an I, give me an N, give me a T, intercept, yes. I'm asking for an intercept. Expected outcome is intercept. So if I want to know intercept, what goes in my estimate statement? Everything! Because everything predicts the intercept, including the intercept. So any statement that asks about predicted well-being, let's do that one. What was it again? Well-being at the end for training. Okay. Nope, not that one. Well-being at the end for training. The thing I'm trying to estimate is intercept, right? That gets my 1. And yes, I believe you can abbreviate int if you want. At the end. What is time at the end? 5. What goes here? 10 or 25? This is the 25. If this time got a 5 and no other time gets a 1, then it's 5 by 5. If this is for the training group, what goes here? 1. If this is for the training group at the end, what goes here? 5. If this is for the training group at the end, what goes here? There you go. So if you're not sure whether it is time squared or time times 2, it is squared if you're predicting intercepts. It is by 2 if you're predicting linear time slopes. Yeah, I've heard of people doing, like Facebook and Twitter during my class, but never audiobooks. I think that's a new level of distraction, right? To sort out the audio from this. So you might be thinking, well, that's great if I have red and green boxes today, but how am I going to not screw this up like next week, right? So how do I not screw this up? Guess how I made sure that I didn't screw this up? Can you guess? Practice? Nope. If practice were sufficient, I would not have screwed this up on Monday. Here's how you can check your own work. How is this model centered? Where is the "you are here" sign? Where is the intercept? At what occasion? The first occasion. And for what group? Control. So if I wanted to know what the intercept should be at the end for training, I rerun my model with a new centering strategy. I put time 0 at the end, and I put control group as the 1 and treatment as the 0. Then the SAS default output gives me that, and I know I haven't screwed it up. So the strategy that I was taught, and I think Amy said she was taught, and maybe a few of you others, of how to get model implied predictions to come out by default, you can recenter your predictors to create a new 0 point, and the estimates will realign themselves. So when you don't have red and green boxes in your life, try to find a way to get the information another way. Does that help? Other homework questions? Okay. Well, that is due next Friday, so you still have like 9 days. I saw that like most of you, I think up to 15 responses on the Qualtrics survey. Thank you. If you haven't done it yet, please do it by next Friday, the 15th as well. I greatly appreciate your feedback, and I will use it in planning not only this course, but what we do in the spring for those of you who'd like to stick around. We do have a little bit more of example 7 to go over, and then a little bit of PowerPoint stuff. So shall we return back to that? See the quadratic example? This will be old hat for you by now. Here we go. Picking up with model 2A on page 12 of example 7. I'm also going to get out the spreadsheet that goes with this to refer back to, as I have made some pictures in here that will help us in understanding these models. Okay. So before I do that, actually one slide about the idea of strategy. So I'm showing you just examples of models and how you would interpret the parameters in the models. I can't tell you definitively what your strategy should be for adding predictors, because it really is context and research question dependent. I can tell you what I tend to do. So what I tend to do in practice is for each time invariant predictor of interest, I run a set of models where it's the only time invariant predictor. So like in this example, if I had age, reasoning, and education, I'd have an age-only model, I'd have a reasoning-only model, and I'd have an education-only model. What that tells me then is bivariately what predictors predict what when all by themselves. Is age related to something? Is reasoning related to something? Is education related to something? I would then combine them into the same model as needed to answer whatever research question I had. So for instance, in cognitive aging, I might want to know, does age still matter after I account for reasoning? If that were the case, I would start with a reasoning only model and then add age. Or I could start with age only and add reasoning, depending on how I wanted to talk about it. If, let's say that reasoning was significant without age, but it dropped out when I put age with it, then I would be able to say, well, yes, reasoning does predict the intercept. However, after you control for age, it does not. So whenever you have a non-significant effect, I think it's useful to find out, is it non-significant now because of the stuff that's in the model too, or was it ever significant in the first place? Ever significant in the first place is what you would find out if the predictor was by itself. Still significant after controlling for whatever else is what you find out when you put them together. How you put them together, really, it sounds like a cop-out, but it's guided by theory, it's guided by questions. And by theory, I mean there's probably some controls that everybody wants you to have, and your paper has to show that your new predictor of interest does something different above and beyond the controls. The controls go first, then your predictor comes in to save the day. I would discourage you from trying to build the best model. That's never going to happen. If you have even more than like 3 or 4 predictors, you and I could approach the data analysis with the same data set and end up at a different best model depending on what we put in when. There is no such thing as a best model. You may have multiple reported models, like this model focuses on these predictors, this model focuses on this other set of predictors. Maybe they kick each other out if you put them both in and they're both worthy of talking about. So all of the strategies that you learned, hopefully, in model building for simpler models still hold here. It's just that you have to think about what they do in each multi-level equation, predicting intercepts, predicting slopes, and slopes of various kinds. So that is to say, the examples that I'm showing you here, I'm just trying to get you to understand what the effects mean. I'm not necessarily saying you should always do it this way. Okay? Fair enough? All right. So quadratic. We are going to go through the same sequence that we did with piecewise so that you get to see everything one more time as a review. I'm starting with an unconditional model where I only have linear and quadratic effects of time. In our previous analyses, we had found that each of those needed a random slope, and so those are in here. This model represents my new baseline because this is all the random intercept variance that there is to be had, all the variance in linear time that there is to be had, and all the variance in quadratic effective time that there is to be had. So I am calculating total R² for it to see how much of the variance in response time is just due to change over time. I'm saving the variance components that come out so that I can see how they each go down after adding each predictor. And I will point out a potential problem with polynomial models here. This is my G correlation matrix. This is the correlation among my individual intercepts and slopes. Do you see anything in there that looks like, uh-oh? Because I see something. What's the biggest correlation you can have? 1, yes. What's the smallest correlation you can have, numerically? Right, 0. So an absolute value, it's 1, right? Plus or minus 1. Do you see anything in this matrix that looks like it's dangerously close to that? Yeah, the linear and quadratic slopes. Do you think that time and time squared are related? Odds are good, right? Yeah. So this is the point at which someone would say, well, I should have done orthogonal polynomials or orthonormalized trans whatevers, you know, to make them not related. They're still going to be related. So keep in mind that how correlated your random effects are may lead to screwiness down the road. You can see reductions in linear slope variance that should have been shown up in the quadratic slope variance or vice versa. If these things are very highly related, it becomes harder and harder to parse what is an effect on linear time versus an effect on quadratic time. And in fact, we will see a consequence of that here in just a moment. All right, so total R² is about 4%, the same as it was before. Bypassing this for right now, we'll come back to it, hopefully. I have age in here. Here's my 3 new terms. Here's my multivariate wald test for whether age matters. It's a 3-degree of freedom test. I am asking for what the effect of age is at each occasion. And the age by, and how the age by linear time slope changes by each occasion. So that is one way to think about the effects of age, is how they vary over time, as well as how the effect of time varies by age. Here is my story. This is my reference growth curve. For whom? Age equals 80 in this story, yes. So, an 80-year-old, response time of 1950 milliseconds at the beginning, an instantaneous linear rate of change at the first session of 101 milliseconds a session. What happens to it over time? Which pattern is that? Less negative, yes. So people slow, they improve in response time less as time goes on. The linear slope is minus 121 at the beginning. What does it become at the next session? Less negative by how much? And don't say 13. 26-ish, yes. Closer to 27 actually, but twice the quadratic. Okay. If we do the main effective age, this is the main effective age, meaning it predicts which term specifically. Give me an I. Hey, we got an intercept, yes. And I know that because of these interaction terms. This is the simple main effective age when time is 0, which is at the beginning. For every year older I am when I walk in the door, I am 29 milliseconds slower. Here's the linear time slope at the beginning. What happens to it in older people? More negative. what happens to the quadratic in older people? More positive. So if I were to describe how age affects this trajectory, disregarding the p-values, you're like, picture? Picture, right? Picture, that's how I would describe it. So this is from the reasoning by change model. Do I have an age one? No, I didn't make an age one. But picture is how I would describe it. I'll just do that one for reasoning. But the general trend here is that the older you are, the higher you start out, the faster you decline initially, but the more positive quadratic sort of reels that in more. So it's a steeper trajectory with a bigger deceleration in older people. That's how I would describe it. However, not significant. Because of age's special status, I am going to leave it in the model, all three effects to control for age before looking at reasoning. So here are, here's my total R-square for the three effects of age. Here's my pseudo R-square. 10% of the intercept variance, 3% of the linear slope variance, and less than 1% of the quadratic slope variance. So those are my effect sizes that go with each of those significance tests. Adding in reasoning. Same story, three effects go in. I have what the reasoning effect is at each session, as well as how the reasoning by time interaction changes over time. That's the three-way. Okay. Here's my result. Now let us look at p-values here. If reasoning has no special status, what is your first inclination as to how I might simplify this model? What stays and what goes with respect to reasoning? Effect on the intercept stays. How about the effect of reasoning on the quadratic? Go or stay? This is not a trick. Go. How about reasoning by linear time? Do we chuck it too? Because it's non-significant? That might be one strategy. However, I would argue that is not a good idea. Again, do you think time and time squared are related? Do you think the unique effect of reasoning by time might be different after reasoning by time squared is gone? Could be. So let's, here's my old model. Here's my picture. You can see how I made that. I hate running out of time in class. It makes me so sad. So I take it out. Here's my equation at level 2 on the bottom. This is something that I tend to do that I don't know that everyone does, but I do it because it makes it easy to see what's missing. I try to keep the spacing consistent. So you can tell that all three of the random effects are there, but that there's not an effective reasoning on the quadratic. It makes it readily more apparent than if you just had a pile of equations. But that's my own convention. Let's see what happened. I took out just that term. Dun da da da. Da 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 da. Reasoning by time is now significant. This is for two reasons. Number one, it means something different. This reasoning by time up here, when you have reasoning by time squared, this is the effect of reasoning on the time slope at the beginning. This is the effect of reasoning on the time slope overall. So they change interpretation. One is conditional and one is not. But also look what happens to the standard errors here. 4 versus 1. That's the collinearity issue biting you. So your take-home message here is when you're working with polynomial models or any kind of model where you have very correlated effects of time like this, be careful chucking them all at once. I would go one by one to see what is necessary, because the story may change if you remove terms that are highly correlated. It changes for two reasons. The term itself means something. So in the previous model, time by reasoning is conditional on the first occasion. And so the standard error reflects like that new effect. But it also changes because of it's not competing against the quadratic by reasoning term anymore in the second model. Yeah. So if we look at what, let me go back in the output to the model that had the reasoning by quadratic. Here is what the model with reasoning by quadratic says happens to the reasoning by linear interaction over time. It is initially negative. Reasoning makes your linear time slope more negative at the beginning. It makes it less more negative as time goes on, eventually making it more positive. But look at the standard errors that go with it. You had the most precision in the middle of the data. So the 4 is a consequence of the fact that it's a beginning and a consequence of the fact that this term is being estimated in competition with this other one. The term that we ended up with is closer to the average of these terms in here than what we had before. And let's see if there's anything else. So how I made pictures is in Excel. We've done that before. Education group is exactly like I did before with the same code. Nothing really new there. Education still doesn't matter. Still has no effect size. And because I like you guys, words. So this example is not in the book, so I gave you a results section for each of the sets of models as to how I would have talked about the interpretation of these things. So those are my words. I'm not saying they're right ones, but they're at least something you can start with. All right. Quadratic time models as well. One more brief topic before I turn you loose to do evaluations then. Any questions before I change gears slightly? Okay. So this last thing here that I wanted to talk about briefly is, I'm going to say somewhat controversial. It's actually not a settled question. I have a study under review looking at the answer to this question, and so I have an opinion, but it may be something to where in a year from now I think differently once I know more. So let's go back to PowerPoint here. I'm on slide 16. This was the example we looked at as education as a time invariant predictor predicting the random intercept, the random linear slope, and the random quadratic slope. So here's a question. What if I had not detected individual differences in change, but the whole point of my study was to examine whether this time invariant predictor predicted change? Can I still do it? So what the model would look like is the one on the right there. I would still have my cross-level interactions with the effects of time with my time invariant predictor like education, but they're missing the U's in their lines. So I've summarized this debate for you. I have seen people claim emphatic answers on both sides. Some people would say no. If you did not find individual differences in change, then why are you trying to predict that non-variance? It's really hard to predict a constant. So some people would say this is stupid and you shouldn't do it. The reason you shouldn't do it, by the way, is that without those U's in the model, the standard error that gets computed for the cross-level interaction is different than if they were there. It's going to be smaller. It's going to predict residual variance instead, and it will have a different denominator degrees of freedom in packages that use that. So they think that these cross-level interactions are more likely to be type 1 errors because you don't have the U's in the model. People on the other side of the fence say, well, it is hard to predict random things. It's hard to find random variances, particularly with not a lot of people. So if you have a small study, and the whole point of the study was to predict individual differences in change, even if you can't find random differences, you can still try to find systematic differences. And that's the side of the fence that I fall on. I think you can do this, it just requires more caution. To do this requires new vocabulary. The idea is systematically or non-randomly varying. So let's say that I initially did not have a random time slope, and I'm interested in testing whether groups differ in their change. If they don't, I'd still call the time slope fixed. Everybody gets the same. If group by time is significant, I have a new phrase to describe this, systematically varying. So systematically varying is a middle ground. We told you before that fixed is everybody gets the same, right? Random is everybody gets their own. The purple here is in the middle, and that's why it's purple, by the way, between red and blue. It's not that everybody gets their own, it's that people need their own deterministically as a function of known predictors. In this case, like the control group would get one slope, the treatment group would get another, and people from the same group get the same slope. So this to me seems perfectly logical. The question is, how would you test these things without increased type 1 error? So here are the other situations and the words that I would use for those. And this is the idea that we have come up with, a paper that's under review, is rather than just doing significance tests for your level 2 variances, also compute something called slope reliability. This is an adaptation of a formula that was published in like 1989 specifically for longitudinal studies. This makes it more general to any kind of multi-level design. Slope reliability is the slope variance divided by basically a rescaled residual variance, to think of it as like per unit time. So things that make your slope reliability go up, slope variance, more sample size, and less residual variance. So you can kind of think of this as like an ICC. Broadly construed, what this is getting at is like how much of your slope variance is really slope variance versus the error around the slopes. That's what the idea that this is trying to get at. And we did a simulation that suggested that anytime that you have a slope reliability of about 0.2 if you're using REML or 0.15 if you're using EML, you should keep your slope in the model to test your cross-level interactions, even if it wasn't significant. That kept type 1 error right where it should be. So that's the last part here. I gave you a spreadsheet by which to calculate these things. So I calculated the reliability of the random slopes in this example, and the intercept as well. So for instance, in this piecewise model, the first slope had a reliability of 0.75, and the second slope had a reliability of 0.66. Both of those were statistically significant in this sample. If somehow those slopes weren't significant, but they had reliabilities that big, I'd keep them anyway. So this is much more likely to be an issue when you have very small level 2 samples, not a lot of power to detect significance of the random effects, but you still may have random effects that are sizable in and of themselves. So this is just one additional wrinkle to the story. If you're interested in testing cross-level interactions, make damn sure that your level 2 effects, random effects, don't need to be there. So this is another way to make damn sure. And that's my story. So I'll let you know how the paper turns out. Like I said, it's under review, so we'll see. And I did not ask for anonymous review because I thought, well, that's silly. I'm going to talk about it on the internet. It will all come back. So next week, I'm going to do lab day on Wednesday afternoon, 1 to 4. If you'd like help with your homework or otherwise want to come chat with me, please feel free to stop by. If not, have a great break. Thank you for all of your hard efforts this semester. I really appreciate it. Everybody's turning shit in on time. You guys are showing up. I feel like the questions you're asking indicate that the stuff is starting to sink in. And that's great. So I really hope that I can see as many of you as possible next semester to keep it sinking in and to start doing even more cool stuff, such as mediation and multivariate analysis and adding longitudinal people in groups and all that kind of cool stuff. So now I have to leave the last 10 minutes of class for these ever so helpful evaluations. The people who pay me like for me to do this, so I don't get a choice. Would somebody be willing to take these papers back to Suzanne across the hall? You will? Lovely. All right, so let me pass this stuff out here, and then I have to leave the room per university instruction. So have a pencil. I will be across the hall in my office, and then I will come back once everybody is done to resume office hours.